In Chapter 11, we're going to talk about sequences and series. So today we'll start with sequences. Now, a sequence is a function. Its domain is a set of positive integers. Now, that's important information. It tells us what our input will be. And the variable that we use for our independent variable is n. And then the terms of the sequence we represent by subscriptive variables. And generally we use a, so we would see a sub 1, a sub 2, a sub 3, and so on. Now, when the formula for the nth term is known, then we represent the entire sequence by placing braces around the formula. And we see that kind of notation in the first two examples. So we're going to look at finding the first 5 terms of the sequence in the problems that we have. So remember that n starts with 1. So for problem 1, a sub 1 will equal 1 over 1 plus 2, or 1/3. And a sub 2 is 2 over 2 plus 2, which is 2/4, or 1/2. For a sub 3, we would have 3 over 3 plus 2, which would be 3/5. A sub 4, 4 over 4 plus 2, so 4/6, or 2/3. And then a sub 5 would be 5 over 5 plus 2, or 5/7. So the first 5 terms of this sequence would be 1/3, 1/2, 3/5, 2/3, and 5/7. So if you'd like, try problem 2 on your own and then check your answers. But problem 2, we encounter that -1 raised to the n power, and so what that means is that our sequence will have terms with alternating signs. So for the first problem, we would have -1 raised to the first over 1 plus 1 or 2 times 1 plus 2 or 3, which would give us -1/6 for the first term. Continuing that pattern, a sub 2 would be -1 squared, which means that our answer then would be positive, over 2 plus 1 or 3 times 2 plus 2 or 4, which would give us a positive 1/12. A sub 3, -1 cubed, over 3 plus 1 or 4 times 3 plus 2 or 5. So now we're going to have a negative 1/20. A sub 4, -1 to the 4th, over 4 plus 1, so 5 times 4 plus 2, which would be 6. So this time we'll have a positive 1/30. And a sub 5, -1 to the 5th, over 5 plus 1, which is 6, times 5 plus 2, or 7. So now we'll have a negative 1/42. So notice that with the odd values of n, we have negative answers, and for the even values of n, our terms are positive. So a sub 1 would be -1/6, a sub 2 positive 1/12, a sub 3 -1/20, a sub 4 positive 1/30, and a sub 5 negative 1/42. Now in this next example, we need to write down the nth term or the general term represented by the pattern that we're given. And so we're given the first 6 terms. We need to find a way to represent that pattern using n. So remember, we start n at 1. So in this case, a sub 1 is 1, a sub 2 is 4, a sub 3 is 9, and so on. And we need to find the general way to represent that. So what I notice is that if I take n, or my subscript, and I square it, I get the value of the term. So I can say that a sub n is equal to n squared. For problem 4, I have alternating signs. Now that tells me that I'm going to have -1 raised to some power. And now the 3, which is a sub 1, is positive, so I don't want to take -1 and raise it to the n power. I need to raise it to the n plus 1 power. So I would have 1 plus 1 or 2, which would give me a positive value. And then a sub 2 is negative 6, a sub 3 is 9, and so I noticed that to get from n to the term, I would multiply by 3. So this I could write as 3n, and that would be the value of a sub n. So a sub n would equal negative 1 raised to the n plus 1 power times 3n. For problem 5, a sub 1 is 1/2, a sub 2 is 3/4, a sub 3 7/8, and so on. So I want to find a sub n, and what I notice is that in the denominator, if I take 2 and raise it to the n power, I will get the value of the denominator. So I would have 2 to the n in the denominator, and in the numerator that's 1 less than the value of the denominator. And so I want to take my 2 to the n and subtract 1 to represent the numerator. So in this case, a sub n is equal to 2 to the n minus 1 over 2 to the n. Now in problem 6, we have what's called the Fibonacci sequence. And this one is a little strange at first, but what we notice is that the first term is 1, the second term is 1, and then every term after that we find by adding the two previous terms together. So we write that as a sub n minus 2 plus a sub n minus 1. And what that means is that to get the 2, we take the 1 plus the 1. So 1 plus 1 is 2, 1 plus 2 is 3, 2 plus 3 is 5, 3 plus 5 is 8, 5 plus 8 is 13, 8 plus 13 is 21, and then so on. Now another thing that we're going to look at is a factorial. Now n has to be an integer greater than or equal to 0. We have a notation for n factorial, and that is an exclamation point, and we define it to be 0 factorial as 1, 1 factorial as 1, and then n factorial is essentially taking all of the numbers, all of the integer values up to n, and multiplying them together. So for example, 4 factorial would be 4 times 3 times 2 times 1. And then we could actually do that multiplication and get 24. Where 7 factorial would be defined to be 7 times 6 times 5 times 4 times 3 times 2 times 1. Now that leads us to another formula for n factorial, which is n factorial is equal to n times n minus 1 factorial. So what that means here is that if I look at this much, the 6 times 5 times 4 times 3 times 2 times 1, that's another name for 6 factorial. And so what we have would be 7 times 6 factorial. And since we used the term before that, that's called a recursive formula. So whenever you have a formula that uses the term before it, we call that recursive. And we're going to look at some recursive definitions. But let's look at problem 7 first. And we're going to evaluate this using our calculator. But I'm going to start by saying that if I have 5 factorial over 3 factorial, that would be 5 times 4 times 3 times 2 times 1 over 3 times 2 times 1. Now these will cancel, and I'll be left with 5 times 4, or 20. So this is really 20 times 8 factorial, and that will equal 806,400. Now there is a button on our calculators that will do that, and we can look at that in class tomorrow. Let's look at some recursively defined sequences, and we want to write the first 5 terms. And so it says, have the first term of this sequence be -2, and then every term after that take the n value and add the term before it. So that would lead us to this. A sub 1 is -2. A sub 2, so n being 2 here, would be 2 plus a sub 1, which is negative 2. So we would have 0. A sub 3, take n, which is 3, and add the term before that, which is 0. So we would have 3. A sub 4, take n, which is 4, add the term before that, which is 3, and that would give us 7. A sub 5 would equal n, which is 5, plus the term before that, which is 7, to give us 12. And so the first 5 terms of this sequence would be negative 2, 0, 3, 7, and 12. For problem 9, this time a sub 1 is capital A. A sub n is equal to r times the term before that, where r isn't equal to 0. So a sub 1, capital A. A sub 2, r times a sub 1, which is capital A. A sub 3, r times a sub 2, which is r, capital A, which gives us r squared times capital A. A sub 4 would be r times a sub 3, which is r squared, capital A, and that simplifies to r cubed, capital A. And a sub 5 would be r times a sub 4, which is r cubed, capital A, and that would give us r to the 4th, capital A. So tomorrow in class we will go over how to use our graphing calculator to find a factorial, and also do problem 10 as an example. So tonight what you should do is check Edmodo for the problems that you are assigned that you can do after going over these notes.